Hello, I'm Mark Unkefer, Executive Director of the Fiber Optic Sensing Association, and welcome to this November webinar, Distributed Fiber Optic Sensing for Above and Below Railroad Monitoring, which highlights one of the really significant use cases that is available with fiber optic sensing. And we have two companies working together that will be presenting for this. From AP Sensing, we've got Lena Tubiana, and from Sercel, we have Helen Ermantek-Seva. I think I a little bit mangled that, but we look forward to hearing your presentation, and then we'll be taking questions at the end. Thank you.
Thank you. Thank you very much, Mark, for the introduction. Yeah, actually, it was a small mistake in our names, but no worries. So good morning, good afternoon, good evening. My name is Lena Urmantseva. I work for AP Sensing with almost already 2 years of experience in AP Sensing. I will kick off today's session, and later my colleague from Sercel, Lena Tubiana, will take the stage. And first of all, we would like to thank Fiber Optic Sensing Association for providing us with this opportunity to participate in this webinar and share some examples of how fiber optic sensing can be applied in the railway infrastructure. So some time ago, my colleagues from AP Sensing participated in the FOSA webinar with the topic Advanced AI Techniques applied to rail monitoring using fiber optic sensing. They delved into the difference between classical data evaluation and artificial intelligence, the principle of deep neural networks, and presented some case studies on how AI can be applied into the railway monitoring. So building on that, today, together with Ellen, we aim to provide a more detailed exploration of various applications of fiber optics in the railway monitoring. And before we move further, if you haven't subscribed to the Fiber Optic Sensing Association channel on YouTube, I highly recommend to do so. So in this webinar, we will offer an overview of both companies, AP Sensing and Sercel, detailing the technologies that these companies provide and delving into various case studies that cover both above and below the rail track. So following AP Sensing part, I will hand over to Ellen. She will present the Sercel and introduce innovative approach on how trails can be utilized to understand what's going on below the ballast. So AP Sensing is a global leader in distributed fiber optic sensing. We provide distributed fiber optic sensing instruments and solutions for various applications. Our headquarters is located in Böblingen. It is a small city in southern Germany near Stuttgart. So although officially AP Sensing was founded in 2007 as an independent company known now as AP Sensing, our roots and experience in fiber optics extend far into the past. So actually, AP Sensing originated from the fiber optic measurement business through several spin-offs. The first instance occurred in 1999 when part of Hewlett-Packard's business, including fiber optic test equipment, transitioned into Agilent Technologies. And in 2007, the second spin-off occurred when the fiber optic business separated from the Agilent Technologies to form the AP Sensing. So we operated the international companies with over 100 employees across 4 continents. AP Sensing holds all necessary ISO certificates in quality management, environmental management, work safety management, along with different important in the industry's certifications. So as I said, AP Sensing is a global organization, headquarters in Germany, but around the globe we have several offices, operational and sales centers. So we have a facility in the UK in Basingstoke. We have sales centers covering our activities in North and South America, Middle East, Far East, including China, Korea, Singapore. So the global presence helps us to provide excellent service and support our clients worldwide. Our main technologies that we're developing are distributed fiber optic sensing instruments, including distributed temperature sensing and distributed acoustic sensing. Within each of this category of these instruments, there are a diverse range of variants. So for DTS, for example, we provide multi-mode, single mode monitoring, utilizing different number of optical channels, as well as single and dual-ended solutions. Our DAS instrument is a phase-based systems that offers quantitative data interpretations. It stands with an outstanding signal-to-noise ratio, and a great performance utilizing just a standard fiber. Notable features of our DAS includes, for example, configurable gauge lengths, edge computing for real-time processes optimizations. And Sensing actually is not only a manufacturer of the distributed fiber optic systems, we're also a software company, so we provide powerful configuration and analysis software tools. And these software tools extend our services beyond the instrument to the data interpretation and data analysis. So at Sensing, we operate in various markets and applications. Here you see the list of areas where we work. We're providing a wide range of services through our instruments and solution. And among these markets, fire detection, of course, mostly, of course, with distributed temperature sensing systems, power cable monitoring, utilizing not only DTS, but also DAS, pipeline monitoring with the demand of both DTS and DAS. We also work in the oil and gas upstream application, different geo-related application, and of course, we work with our systems in the railway industry, so the topic of today's webinar, including such applications as train tracking, asset condition monitoring, cable theft, intrusion detection, and tunnel monitoring. So before we delve further into the specific examples of application in this rail industry, let's just take a moment to explore the concept of distributed acoustic sensing technology. So on this slide, you can see the schematic of the DAS measurement concept and the picture. On the right side, you can see the picture of typical spectrum of backscattered light with Raman bands, anti-stocks, and stocks that are utilizing in DTS systems, Brillouin for DTSS systems, and Rayleigh, which is the foundation for the DAS. So the idea of the method, we plug a fiber, here's the representation of the fiber into the DAS. The instrument send the laser pulse into the fiber. Fibers are not perfect. There are always very, very tiny microscopic defects that randomly spread along the fiber. And when the light pulses propagate along the fiber, part of the light will be subjected to the Rayleigh backscattering. And this backscatter light is going back to the system, and the interrogator analyzes this backscatter signal. The position of the acoustic events that affected the fiber can be determined by measuring the temporal dependence of the returning signal, like it's in the radar echo. So what will be if we place this description of DAS concept in the context of the railway and railway monitoring? Of course, we will need a DAS system, and of course, we will need a fiber optic cable. So actually, when we discuss in railway monitoring, the availability of the fiber is not typically an issue, as there is most likely there is an existing trackside telecommunication cable infrastructure, like it is shown on this picture. Here's the cable in the trough, and we just can utilize existing fiber optic cable. We do not need to deploy any special fiber, and thus allows us to transform the standard cable to a sensing cable, and enables to utilize DAS in various areas in the railway infrastructure, like shown in this picture. For example, train location, speed direction monitoring, flat wheel detection, natural hazard detection, short circuit localization detections, and many natural hazard detection, and many other applications. Fire detection is also something about fiber optic, but since it's about DTS, we're not going to cover in today's webinar. So since I will be showing several case studies on DAS data and how this data can be interpreted and presented, I just would like to start with very simplified explanation on how DAS and how the fiber works in the context of railway monitoring and what kind of data we can see. So let's consider this simple example: the rail track, the fiber along the existing fiber along the rail track, DAS connected to the fiber, DAS connected to the laptop. If, for example, we will have a train passing along the rail track, what we can see. So the typical visualization of phase DAS data is this waterfall plots. On the horizontal axis, we see the distance. On the vertical distance axis, we see the time. So actually, these blue lines, dark blue lines, it's a signal not from the one train. It's a signals from two trains. One train that goes passing this distance without any stops, and another train, you see this interruption, just train stopped somewhere at the train station. So, and analyzing the whole frequency band that we got acquired with the DAS system, we can subdivide this frequency band into different frequency, analyze them, and identify different things that we can meet, let's say, along the rail track. So, for example, we can identify the tunnels, these dark blue spots along the train line. It's a bridges. These fixed crossings, fixed at one distance but changing with the time. These are cars that crossing the rail track. And of course, we can extract the signal from train itself. So the result of this detailed data analysis in combination with AI can be can be utilized for the live train tracking with the DAS system. On this picture, you again see the waterfall. On the horizontal axis is the distance, and the vertical axis is the time. And here you see signals from the different trains, signals from the highway crossing, from the motorway, from the sawmill. And on the right side, you will see the map. And I will start playing this video. And you see on the map these dots that are moving along the rail track. These are trains with their unique information that was acquired from the analysis of the DAS data. Yeah, so the main outputs of DAS live tracking are train position, train length, velocity, acceleration, unique trains IDs, unique tracks IDs, since we can split the information that we receive from the train and that we receive from the track. Can we somehow prove this information that we're receiving from this fiber optic cable? Yes, so there are several technologies that are available to measure the train position speed along the fiber, along the railway track. One of them is the optical odometry. So here, just here's the picture showing how the camera is placed on the windshield of the train. And here on the picture, we see what kind of picture this can be received with this camera. So the camera is pointed on the track, and special algorithms can identify the exact location on the track. And here you can see the bird eye view of the track. And comparing the results of DAS live tracking and optical odometry results, we see that these results are match quite well. So we're providing very accurate GPS position, speed and length of the train utilizing DAS data. The positional accuracy, it's the first meters. DAS technology was proven for 2 parallel running tracks with 1 fiber. It works well with fiber installations in tunnels or in the bridges. And it works well for high-speed trains and for low-speed trains. And here on this graphic, you see the comparison of the speed of the trains defined by fiber optic sensing. It's a red line, and blue line from the video. Even it's a low speed train, we see quite close match. So taking railroad asset as an example, distributed acoustic sensing can be also excellent tool not only for train tracking, but also can be excellent tool for the monitoring of the different railroad assets. So for example, utilizing DAS data, we can efficiently localize short circuits along the railway. So here the results of test studies along the rail track, and here two pictures from actual catenary and the whole view and the zoomed view of this catenary system. So I will start playing the video, and you will see what happened. You see this flash, and here on the left side of this slide, you can see how it looks like on the DAS data. So this typical V-shaped signal shows us that we could detect the short circle, and we the idea that we localize these short circles, short circuits, and the operator of the rail track can receive the information about the event that happened and exact localization of this event. Another railroad asset that can be monitored utilizing DAS is just track itself. Part of the track, here on this picture, you can see part of the track around 2 kilometers. And this yellowish line is the signal from the train passing, only from one train. And the signal is quite uniform, even though the train is passing different areas along the track. It's passing switches, some train stations, but one area with a bit blurred weak signal is different. It differs from surrounded areas. So, and this phase signal comparison along the tracks helps us to identify some changes in the track bed. Here, just another representation of this zoomed interval. It's an average channel, phase channel signal, and we really see that in this area, these red dots are different from what is around, let's say, this area. So therefore, the DAS can be just a great tool for predictive maintenance. So we already can detect something and take some measures to check what's really going on there. Other assets that can be monitored with the DAS and fiber are rolling stocks, as we can split the signal from the rail track and from the train. For example, when there is a flat wheel, it generates a distinct acoustic signature due to some different shape of the surface of this flat wheel. These irregularities lead to vibrations and noise when the flat portion of the wheel repeatedly touching the rail itself. So here on the left part of the slide, you can see signals from two crossing train, and we see in the middle part, marked with this dark dashed line, this a little bit white signal. So this is a signal from the flat wheel, and we can represent this data a bit in a different way and then normalize to the whole signal, and we see this peak, and so how it looks like in real life, this crack on the wheel. And this information gathered from the DAS can also contribute to maintenance planning and helps operator to fix and schedule maintenance activities more effectively. So DAS also can help us to monitor various third-party interference activities along the rail track when, for example, it's about the theft of the cable that is connected to the DAS. So here on the right side, you can see the whole DAS signal that we received during this cable theft test. And I will start playing the first video. When the person who is simulating this cable theft, he's pulling the cable and he does some breaks. And then here again, pulling the cable and with some rest periods in between pulling. We clearly can see that the signal from pulling and restings are different. Another video I'm starting to play. It's a cable theft with a bit different motions. It's a kind of jerking motions, and we see that on this waterfall that the data that we receive from these jerking motions are different from what it was before. So therefore, this is really helpful tool to understand that there are some third-party activities are going on along the track. Yeah, and we can prevent the property damage and consequences from this kind of activities. Yeah, so gradually we are moving towards to the events that can approach the fiber optic cable, not from the above the surface, but from the below the surface. So what kind of acoustic events can be detected from the below the surface? It's seismic waves, of course. And the seismic waves can be generated by different events like earthquakes, explosions, large landslides, and etc. So seismic waves are divided in two main type of waves that are travel into the surface or into the Earth's surface or along the surface. Here, very nice animation that represent these different types of waves. So here you see the waves are traveling through the surface, let's say from the earthquake event, and another type of wave that traveling along the surface. And here just a seismogram that detect these seismic waves. So I would like to illustrate how the seismic waves generated by earthquakes can be detected by the DAS system using examples of two devastating earthquakes that occurred this year, one in February in Turkey and another one in September in Morocco. So here you can see some information about these earthquakes. There was very high magnitude, but at different depths, and we detected these earthquakes, but they thus located in the Switzerland along the rail track, and you see that the distance between the earthquakes location, epicentrum, and the DAS in case of earthquake in Turkey is 2,600 kilometers. And in case of earthquake in Morocco, it was around 2,300 kilometers. So here we can see two waterfall plots detected from the earthquake from Turkey. Distance on the horizontal axis and time on the vertical axis. And this red signal, it's seismic waves that were detected by the DAS. And we see so we do not see body waves really clearly, but we see the arrival of surface wave, and we see arrival of some waves during the aftershock events. And here just another representation of this utilizing just one of the DAS channels, like we used to see this data on the seismograms. Again, you see, we couldn't really identify body waves, but we can see the surface waves arrivals. If we look at the Morocco case study, so here a bit more zoomed waterfall plot, just 500 meters and 5 minutes, but also we could detect the seismic waves arrival. And here just another representation utilizing one of the DAS channels. Here we could see more clearly primary, secondary waves arrival. And again, the more signal came from the surface waves. So the detection of the earthquakes by the dark fiber connected to DAS provides valuable input for the earthquake awareness systems and can enhance existing earthquake maps because we have dark fibers everywhere. And detecting and analyzing seismic waves, specifically surface waves with the DAS, and understanding the results we can obtain from this data is a really fascinating topic. So to explore further into this topic, I will hand over this part to my colleague from Sercel, Hélène Toubiana, who will provide additional insights into the seismic waves. Please.
Yes, thanks, Lena, for the transition. That's perfect transition. So I'm Hélène Toubiana, and I'm a geophysical engineer with 15-year experience in seismic imaging. And today I will speak about what can be done with the fiber optics and the system below the ballast, thanks to seismic waves. I'm working for Sercel company, and historically Sercel is design and manufacturing equipment for seismic acquisition and provide geophysical processing for natural resources exploration. We have 1,050 employees worldwide with 800 engineers. And we are a part of CGG Group, which is a leader in seismic imaging. Next, please. Sercel is a leader in seismic solutions. Sercel creates, produced, and integrates sensors for high-fidelity seismic imaging, like high-sensitive accelerometers and helically wound fiber. Maybe no one knows about this fiber. Its particular fiber is for 1 meter of cable, you have 2 meters of fiber. It allows to have a more sensitive in every direction and to spatially reduce the gauge length. Sercel also develop geophysical software and services. These sensors and services are used in different domains. Next. The most important market of Sercel is the exploration of natural resources, as I told you before. We deploy sensors at the surface and we induce seismic wave with vibration track to image the subsurface of the Earth, like a medical imaging. The same methodology can be used for energy transition, for carbon capture evaluation or geothermal well positioning as wind farm. And also in the infrastructure monitoring, which is the topic of today, like structural health monitoring of bridge or ground investigation for building construction and the railway industry. Historically, Sercel worked with SNCF, the French railway company, for decades to image the near surface below the railway. Next, please. One of their concerns are the instability that appear below the railway. Indeed, subsidence and sinkhole that can appear at the surface, and the potential consequence that could obviously be dramatical, as you can see on the picture. But we can wonder what is the origin of this phenomenon. Next, please. This phenomenon is an impressive conclusion of slow process of underground decompaction, coming from a natural and anthropologic origin. It starts with decompaction, then cavity growing with a subsidence, and finish by a sinkhole, which is the dramatic event. It can take years to develop. The motivation of our work is to find a method to prevent this accident by detecting it as soon as possible. But how? Next, please. For this, we decided to develop a dedicated methodology based on the use of seismic waves generated by the train. Indeed. First, I have a question for you. Have you ever felt the ground vibrating below your feet when a train is arriving? This can be a powerful passive seismic source available for imaging. You can see on this picture, above the top picture, a train is passing on the railway and emitting seismic waves. This wave can be recorded with accelerometers in yellow or DAS system in red. This seismic wave can be used to image the near surface below the railway. As you can see on the bottom graph, the surface wave look like sea wave, rolling on below the surface, but on more complex dispersive behavior. But what is the dispersive behavior? Let's decompose this surface wave at different frequency. Next, please. Next, yes. If we decompose into frequency band, we can see that the high frequency content of the near surface scans the very near surface. Lower the frequency, larger the wavelength, deeper the penetration, higher the propagation velocity, and faster the propagation. That is what we call the dispersion behavior, and we can measure it thanks to DAS, or accelerometer. And after an inversion process, we can retrieve a velocity model of the near surface rocks. Stiff and soft area will respectively appear as fast and slow velocity spots. That's how we can detect a zone under decompaction before a sinkhole occurs. Next, please. So the processing flow for this study will be to record the signal along the railway, thanks to DAS or either, then detect the dispersion curve, pick it, and run an inversion to obtain a velocity model of the subsurface. Next, please. Let's present a typical project of underground investigation. A huge sinkhole occurs on this railway, as you can see. It has been rapidly filled with concrete, and our services has been required to detect other potential cavity after maintenance. Seismic sensor has been deployed, and after processing, velocity model has been interpreted. Next, please. Here's the result. What can you see? It is an image of the underground. Seismic wave velocity in depth, up to 25 meters, under the railway. Horizontal axis is the distance along the railway, and in vertical axis, the depth. The color represents the seismic wave velocity. We can see in brown the bedrock at 15 meters around, above in green the embankment, and at the surface in blue the ballast. However, in the middle of the section, slow velocity in dark blue is highlighted in the embankment area. That's a danger zone that has been identified. This services was provided by using accelerometer for a few years now. But for many reasons, accelerometers are not adapted to be deployed in the long range. So we were thinking, why? What about DAS? Can we use that for the same application? Yes, there is a DAS opportunity. Railway are linear assets, often equipped with telecom fiber, as Lena said previously. We wonder, can we use this fiber with the DAS system to perform the same image? Let's see it through different case studies. The first case study is about a project that has been done with SNCF on a high speed line. It's an area characterized by ballast instability. First target of this project was to identify if there is instability due to decompaction, and the second target was to benchmark and assess the capability of DAS to detect this decompacted zone. Next, please. As the deployment occurs during the night, we prefer to use the Lego to show the acquisition design. Some accelerometer has been deployed every meter along 400 meters. And the result will be compared to different kind of fiber that has been deployed. A straight fiber has been buried, an helically wound fiber, which is, as I said previously, a specific fiber that can double the resolution because we have double lens, and also the dark fiber that's in the concrete duct. Let's see the result. After one day, only one day, of passive monitoring, and of course the associating processing, we obtain this F-wave velocity until 20 meter depth. As previous example, in x-axis, the distance, here 300 meters. Y-axis, the depth. And in color, the velocity, S-wave velocity. What can we see here? In brown, the bedrock, it's a hard rock. And in blue, the slow velocity. You can see that the bedrock is not continuous. And we can see a decompacted area. In this results, we can clearly see this decompacted area in the rate cycle for every acquisition system, ranked by resolution capabilities. The helically wound fiber first, high resolution with accelerometer on the top, thanks to the short spatial sampling, because we put it every 1 meter. Then the helically wound cable for shortened spatial gauge lengths. After the buried fiber, which is well coupled, and even the telecom fiber. So every of them are able to detect and image this decompaction area. Next, please. The last case study is about the dark fiber capability. As mentioned previously, we are able to detect the decompacted area with a low resolution. So we wanted to know what can be done and which lens can be done with telecom fiber. So the last case study, we just plug a DAS interrogator into a dark fiber that already existing into a concrete duct. And we did the same analysis on 2.5 kilometers of telecom fiber. We record DAS during 1 day, approximately 20 trains recorded. And after a processing step, we get this kind of velocity model up to 50 meter depth with bedrock, substratum, and embankment. So in this analysis, we don't see any cavity problem. However, we face to dark fiber limitation in the center of the section. The center of the section could not be processed because the fiber was laid on the ground, as you can see on the picture. However, so with telecom fiber, the good news is we have really reliable geological interpretation consistent with geological a priori, but with an existing blind zone due to aerial fiber deployment. But that's good opportunity to monitor and identify zone with potential risk because the fiber is already there and we just have to record the data. If I speak about the monitoring, here you have an example of monitoring results. In the east of France, this area has been monitored during 3 years now. And due to a decompacted area in the center of the section, the blue one, as you can see here, we have a permanent monitoring and 1 velocity model per day. If we analyze difference every 3 months, we can see that in the middle part of the section, that has to be monitored, after 1 year, this part remains stable, no major difference. But on the western part of the section, the difference after 1 year has a decrease of velocity, if you see it on the difference. That means that in this part, we have a start of decompaction of the soil. So this monitoring can be really useful by looking at the difference of each section and to monitor the risking area, especially now due to climate change. So therefore, to scan and evaluate what's happening below the railway, we show that the telecom fiber is a good opportunity because it's already there to have a big picture of what's happening below the ballast. A scan of a long distance below the railway can be done with cost efficiency. And if we want to have more resolution, we can use a dedicated fiber, straight or helically one, and can be buried to better couple in some risky area. And finally, accelerometer can be used to zoom into a small distance to have high resolution image and optimize a concrete injection. So finally, our service is on-demand acquisition, coming with an interrogator just by recording data during at least 1 day or minimum 20 train passing, then process the data and interpret velocity model, as I showed previously, with evaluation of soil decompaction on risky area. The quick evaluation can be done every day, weeks, months, years, as needed. So to conclude, the railway monitoring is important in today's environment, particularly the capability of train location, track condition monitoring, and hazard detection. Use of fiber optic open numerous opportunities for above and below the railway monitoring. We show that existing trackside telecommunication and fiber optic signaling cable can be repurposed into sensing cable, or alternative dedicated cable can be installed to enhance the railway protection. Next, through this webinar, we've demonstrated the particular application of existing telecommunication cable for real-time train tracking and assess condition monitoring. This application supports condition-based maintenance, strategic, and contribute to prevention of potential failure. Furthermore, advanced seismic method using DAS present a significant opportunity for the identification and monitoring zone of danger prior to detection of the problem from the surface. So thank you everyone for your attention, and thanks the FOSA Association for this opportunity.
Thank you very much, and we will have we already have a number of questions, but let me just kind of lead. First of all, explain that the question process is in the chat box to the right, and that can get opened up, and you can type in a question. But we do have some already. So one question is what is the longest distance along a rail track that you can monitor with one system?
Lena,
yeah, I can take this question. Yeah, it's actually an interesting question. Yeah, so I'll turn my camera. Yeah, depending. So the DAS system can work at really long ranges, but depending on what kind of data, what kind of frequency you want to get for the further analysis, there can be limitations. Yeah, so we can work up to 70 kilometers, we can work up to 100 kilometers, but if there is a specific range of frequency that you need to receive, there will be limitation because of the physics. Yeah, so we cannot send very high pulse rates into the very long fiber.
So a related question, which I guess would be categorized as kind of an installation question, is how close to the track does the fiber need to be? And does the condition, are there some specific considerations about the nature of installation that affects whether or not you can use it to detect events along the track?
So all these case studies that we showed, they were mostly with the existing telecommunication fiber in the trough. So at 1 meter, 1.5, 2 meters from the track. Yeah.
And for the seismic imaging, actually, the main concern will be the coupling. So if even if we are a bit far, 1 meter, 2 meter, even more, if we have couple, we can still perform an image.
Now, following up on the question relating to, is there typically dark fiber or fiber available along railroad tracks? Is that something, or is it something that you need to get installation for?
So the fibers that we were talking about, it's the fibers that were used for the telecommunication purposes. Yeah, so we just repurpose, let's say, this telecommunication fiber, which is always in the infrastructure of the rail track itself.
Yeah, but just to complete, Elena, this telecommunication fiber has to be non-used. there is always some telecommunication cable that has not been used in this concrete duct that can be used for another purpose. But no data has to come through this one.
So related question, and I guess this would be characterized about noisy areas. So areas where there's a lot of activity going on at the same time. How difficult or how is it possible to tease out particular events that you're detecting when there's other activity going on?
There should be more data acquired, I guess. Yeah, just to be able really to identify the events that we want to analyze, let's say. Yeah, so it cannot be done with just one data set. Yeah, of course, the more noisier data, more activities in this data, of course, more data we will need to really catch these events. And
so essentially with the software, you're able to tease out what are sort of unrelated events that you're not trying to track and pick out particular events. What is the peak power of the pulse that is sent to the fiber under the test?
Peak power?
I guess basically, I guess that's a question about the laser. Is really go ahead. You can answer that, I guess.
Yeah, so the laser that we use is the laser 1 class, but peak power, sorry, but I cannot give the number now. Yeah, around 200 milliwatt at the start of the fiber, something like this.
Fair
yeah, and the bigger, let's say, this fiber you monitor, this it will decrease with distance.
So the next question is, seems the weather events like heavy rains, flooding can accelerate decomposition and subsidence. How difficult it is, can you capture rapid changes like that happening essentially in real time?
Yes, kind of, because for example, on Eastern France, we have a system that is working every day. So we have a picture about the underground every day, and we can identify if there is a big change.
So let me see. The next question is, how much time do you need between data acquisition and the preparation of the final velocity model of the subsurface?
Actually, to have a quick evaluation, we will need at least 20 train recording, so it will depend of the traffic. And for the acquisition, for the processing, it will depend of the geology. It can take a few days, at least, and interpretation 1 day. So in total, for the quick evaluation, it will take less than two weeks for the first scan. But if we rescan the same zone, since we have already all the parameters for the processing, it will take only 2 days.
So I have a specific question, I think that relates to Poland, which is, have you got any case studies with using existing dark fiber and cables buried in ducts at a depth of 0.7 meters? And the questioner references, I guess that is used in Poland. So I guess this is a question of using ducts that are buried somewhat more than is customarily the case.
Could you please repeat the question? I'm not sure that I well understand the question.
Well, the question relates to when fiber optic cable is in ducts that are buried somewhat greater distances. I understand they references 0.7 meters, but a somewhat greater distance than in other areas. And I gather from the questioner that this is more typical in quote unquote telecom reality in Poland.
So you mean that it will be below the ballast or something like that, like a deep buried fiber?
Right. Yes.
Yeah. So for this case, we could image, but the zero elevation will be at the elevation of the fiber. So at the zero will be the depth of the fiber. I don't know if I well understand. We cannot have any information up to the above.
Sure,
The fiber.
and I think this next question captures the global nature of the webinar, because it's not one that we would think of in many countries, but can we detect elephant movements near railroad tracks?
Elephant?
Yeah,
Elephant movements.
Is it
I think
a
I
third-party
needed to get,
interference activity?
I needed to read that twice, and I can probably answer for that, which is that if you've captured that in the past in the software, you could detect the unique signature of an element movement, right?
Yeah, but
Yeah.
I definitely yes, no.
We can detect elephant that's crossing the rail track, of course.
So I can imagine that's the India Railroad is probably a not comic consideration for them. Are the results of on-demand S-wave analysis after 20 trains, 1 day, comparable to the accuracy and or reliability to ground penetrating radar scans?
Can you repeat?
I sure
What is
will.
the quick? Yeah.
Are the results of on-demand S-wave analysis after 20 trains / 1 day comparable to the accuracy and or reliability to the ground penetrating radar scans?
Yeah. It's of course it is as accuracy, and the major purpose to use this S-scan analysis will be to have much more deep information rather than a radar where you can have a very shallow information. You will just have the shallow resolution with the radar, and with the below ballast scan, you will have information really on the deeper part of the section, which where there is a decompaction zone, and some often the upper problem is coming from the deeper part of the section of the below ballast. And the GPR scan cannot see that decompaction.
Next question is, can the same acquired measurements be used for other types of monitoring? For example, can the data for short circuit localization be used for geophysical imaging?
Yes, sure. We can use, let's say, one acquired data set along the rail track for many different applications. Yeah, so you sometimes, of course, you probably will need to change the acquisition parameters, but in general, no, we can acquire the data set and then use for short circuit localization or for this below ballast scan. It's not a problem.
It's the same data set actually.
Yeah.
And I guess this is a response to our reaction to the earlier question, which is there, quote, actually currently tenders going on for elephant detection with railroad tracking in India, and requirements for more than 25 DAS units currently and more than 60 to 80 DAS units in the next 6 to 8 months time. So clearly this is very much which is not surprising. Obviously, India has a very substantial rail network, and elephants are a consideration. So we will share that marketing information for folks who want to pay attention to that.
Yeah, and I guess elephants will create quite strong signal.
Yes, when measuring dynamic strain, how can you interpret the measurements without having a complete historical data? I mean, can you just concentrate, I think that's the measure in time to make up for a wider window measure, or will you not be able to actually infer signals that are slower? So I guess this is really a question about how the learning takes place for the software. if I'm interpreting that question right. I can capture it again. I think this is where the signal is that being picked up is not one that has been previously identified. How adaptable is the software to be able to identify what the event might be? I think I'm capturing the question with there.
Okay, I can answer for the below ballast scan. Actually, we run the algorithm without any model a priori. So all the results are coming from the velocity that has been propagating into the soil and are coming from the data. There is no a priori. So no, we don't have any input information from outside.
Another question is, can you detect railroad sabotage in real time?
Yes, sure. So we receive the data from the DAS in real time, and yeah, we can identify this as it was shown in the slides like cable theft activities. And yeah, we on the DAS we can set the alarm, so the system will notify the end user that there is something going on, and everything is in real time. Yeah.
And a related question to the elephant, I think in Mexico requests detection of jaguar for Maya train. And the answer was no because of weak foot signal. So I guess the sensitivity is good for elephants and bad for jaguars. And a follow-up onto the follow-up is that evidently for the India use case for elephants, the questioner is already in discussions with AP Sensing for working on that issue. So we're that much ahead of the curve. This, I think, brings a number of the questions relate to sort of the logistics of getting people who joined late or wanted to go back over material. We would expect that this webinar will be posted on the FOSA YouTube channel in a relatively quickly. Usually it's within the same day. Sometimes it takes a little bit longer. So that's available there along with the additional resources that we have for FOSA. Obviously your contact information is available on the final slide. So more detailed or more specific questions, you can try and answer that as people reach out to you. So thank you very much. That concludes this webinar. It's been very informative.
Thank you very much for joining this webinar. Yes, our contacts are on the slides. Please, if there are any further questions, please contact us. And yeah, thank you, FOSA, very much for this opportunity.